The next thing that we need to be able to do with logarithms is use them to solve exponential equations. Now you can use a lot of the same things that we do to solve exponential equations with logarithmic. We're actually not going to study that in this course. It's been moved to pre-calculus. But you are still given logarithmic equations. You would just solve them graphically the same way that you did exponential equations. So exponentials and logarithms are inverses of each other, meaning that we use these to help us solve for a variable that is in the exponent. So if we were looking at an exponential equation that had 6 as the base to the x power, so again, notice that the variable is in the exponent. To solve this, we would need to take a logarithm with a base 6 so that they would cancel, and we would just be left with the variable x. We also have to do the same thing on each side of the equation, and we'll look at a couple strategies for those in just a second. In this example, because my exponent has a base of 3, I would need to use a log base 3 so that those would cancel out and I would just be left with the variable in the exponent. So how do we use this to actually start solving these equations? So there's a few different strategies. One thing that you will start to get a little better with in time is identifying what strategy that you're going to use where. So the first one that I have an example of here is actually one that is really kind of the most simple. So 6 to 3x minus 8 equal to 6 to the 5x minus 17. If we take our log base 6 of both sides, because again, what I do to one side, I have to do to the other, that would allow us to cancel the base of 6, and then we would just be working with our exponents. And we notice that's just a nice, simple equation we've been solving. So I could subtract the 3x from the 5x to get 2x. I could add the 17 to the negative 8, which would give us 9. So x would be equal to 9 over 2. This actually leads us to the property of equality for exponential functions, which simply says that if you have two equations or two expressions that have the same base, then the exponents have to be equal to each other. So basically we just can say, well, because I know the bases are the same, the exponents have to be the same, and then we can just work with the exponents. We don't really have to go through that step with the log. So a couple of examples. If I look at my two equations or expressions, they both have a base of 3. Since they both have a base of 3, I can set the exponents equal to each other and then just solve the equation. So I would subtract x from 2x, subtract 5 from negative 4, and so my answer for that one would be negative 9. Same here, we have 4 to the power of x, 4 to the power of 5x plus 1. Because the base is the same, the exponents are going to be equal. We can subtract 5x from x. We get negative 4x equals 1. Divide by negative 4. Negative 1/4 would be our solution. So those are the really nice simple ones, but then that leads us to the next question: what if the bases aren't the same? So the first thing you always want to look for is, are there anything being added, subtracted, multiplied, divided to the exponential expression? So we want just the exponential expression by itself. We would move things around if necessary. Neither of these examples have anything where we have to move around. We'll look at some of those in just a few minutes. And then we can rewrite the number, meaning the base, as something with an exponent with the same base on both sides. So we're taking a number and rewriting it as an exponent using the same base. And again, this is one that you just kind of have to start to see more over time. So I have 4 to the power of 2x plus 5, 8 to the power of 3x plus 9. Well, they're not explicitly the same base, but I can rewrite 4 as 2 squared, and I can rewrite 8 as 2 to the third, because those are equivalent. I would still raise it to the power of 2x plus 5, and this one would be raised to the power of 3x plus minus 9. So now that the bases are the same, the exponents are the same. One thing we have to be careful about here is that we have to use distributive property. If we have a power to a power, so that's what we have here when we rewrote it as a power to a power exponent rule, which says that those two things have to be multiplied together. So we would need to make sure that we recognize that by using distributive property. And then we just move things around, so I can subtract 4x from 9x, and I can add 27 to 10. And so then divide. And there's my answer. So I haven't done myself any favors with some of these numbers today, but luckily the steps aren't too hard. In this next example, I have 5 and 125. So I don't need to do anything with the 5 because I can rewrite 125 as 5 to the third. And now the bases are the same, so the exponents are equal. I'm going to go ahead and distribute that 3, subtract the 3x, divide by 2, and there's a nice number, x is equal to 3. Now, those are, again, the nice ones, so we're going to get to some that are, a little bit more difficult as we go. So what happens if I can't rewrite the number using the same base? And that's where our change of base formula comes in that we talked about in our introduction to logarithms lesson. So again, I need to get whatever the exponential argument is by itself. So this 28 has to be subtracted from both sides. So we would take 62 and subtract 28, which is 34. And I can't rewrite 34 as a base of 3. So this is where we're going to use our logs. You can either think about taking the log of both sides like we did at the top, or we're really just looping this because these are just like the ones that we looked at when we were rewriting. So log base 3 of 34 is equal to x. Again, if you have a calculator that will change the base for you, then you can just calculate that. But if you're using a standard like 4-function calculator, then you'll have to use your change of base that we talked about. And again, log base 10 is nice because that's what calculators are already programmed to do. So log base 34 divided by log of 3, so 3.2 would be my answer for that one. So again, in this one, they have 10 to the 3x, but it's not isolated. I'm going to have to divide both sides by 6. So 200 divided by 6 is not a nice number. It's 33 and a third. So on the other one, we rewrote it. On this one, I'm going to do it by taking the log of both sides. Again, we would take log base 10. You don't have to write the 10 because that would cancel. That means I have to take log base 10 of the other side to keep my equation balanced. So this would be log base 10 of 33 and a third, which is just a number because remember, logarithms are just giving us an exponent. So 10 to some power equals 33 and a third, and that would be about 1.52. And then the last thing to solve that equation is to divide by 3. Undo that multiplication on both sides. So my final answer should be about 0.507. All right, so here's where we start to use this idea of natural log. So we have Euler's number as a base. But just like before, I need to get that exponential by itself. So for this one, we will want to divide both sides by that 1,500. So 10,000 divided by 1,500 is 6 2/3. So I'm just going to write it as a mixed number. So natural log to undo base e, and we can write it like this. We can do the natural log on both sides. So I get 0.07x is equal to the natural log of 6 2/3. So remember that that's just a number. So I'm going to go to my calculator, find the natural log of 6 2/3, which is about 1.89. And then the last step is going to be to divide by that 0.07. And my answer is about 27.1. Okay. So again, I can't have this plus 5. I've got to subtract that from both sides, so I just have e to some power. We use our rewriting. We would say the natural log of 10 is equal to x minus 1. So I'm just rewriting. Natural log of 10 is just a number. Find that in the calculator. It's about 2.3. Add the 1. So my answer is about 3.3. So I think the hardest part is, kind of learning how to deal with the exponents. Everything else was just solving equations like we've done before. All right, so we've got some operations in here. Now we've got some multiplication and some additional exponential arguments. So in this first example, the base is all the same. All three of those have 2, so we can still use the relationship we were using before. Remember that if we multiply exponents with the same base, we add their exponents. So I'm using my exponent rules on the left side. And then because the bases are the same, those expressions would be equal, or the exponents would be equal. So 4 minus 1 is 3. I add 3 to both sides. I'm going to get 3p equals 2p. If I subtract the p, 2p from 3p, that would be equal to 0. So that one wasn't too bad. Some of it just goes back to remembering your exponent rules. This one is going to use a couple different ones. I don't have a like base here in that I have an 81, I have a 1/9, and I have a 243. Not 81 is 9 squared, right? So again, just kind of start being able to identify that we have some powers related here. 1/9, so remember we have things with a negative exponent. We would rewrite that as 9 to the negative 1. And then 243, just make sure, I don't actually think I can write that one as a power of 9. But what if we could write it as a power of 3? It's 3 to the 5th power. So actually my 9 isn't going to work here. I'm going to have to use 3 to the 5th. I can rewrite 9 as 3 squared. That would still be, let's go ahead and use our power to a power rule. Negative 1 times negative b is going to make that positive b. And then this would be 81 is 3 to the 4th. And that's to the negative b minus 3. All right, so a little bit more work with this one. I'm going to go ahead and use the power to a power rule, which says that we would multiply. So there would be my exponents. If I'm multiplying, I add. So negative 4b minus 12 plus 2b equals negative 5b. Combine like terms. I can add the 2b to the negative 5 to make that negative 3, divide both sides, and so the answer is 4. So that's a little bit more work. I would probably say something like that would be easier solved graphically, but we can solve them algebraically.